Welcome to part 2 of this week's online lecture. In part 2 we will use symmetry to classify polyatomic molecules according to their rotational characteristics. So let's have a look at polyatomic molecules. Here's a water molecule. I can identify its rotational axes, and for this molecule, because it is nonlinear, there are 3 rotational axes. The rotational axes still go through the centre of mass, but notice that the centre of mass for water is not the centre of the oxygen atom. It is slightly displaced downwards because the hydrogen atoms are below the oxygen atom, so the centre of mass and the rotational axes are going through a point that is below the centre of the oxygen atom. I have labelled the rotational axes A, B and C, and thus I have labelled the associated moments of inertia around these axes as I sub A, I sub B and I sub C. I'll be describing how we choose which one is A and which one is B and which one is C in a little while. If the polyatomic molecule is nonlinear, it will have 3 rotational axes. If it is linear, it will have 2 rotational axes, just like the diatomics. All the rotational axes go through the centre of mass of the molecule. This choice of rotational axes is quite a natural choice for the rotational axes of a water molecule, as I'm sure you would agree. Both the IA and IC are in the plane of the water molecule, with the plane intersecting all of the atoms. IB is perpendicular to the plane of the molecule. That seems like a natural choice. In other cases, it can be that the choice of the axes can be quite arbitrary. They don't have to be perpendicular to one another, for instance, and I'll illustrate that with the benzene molecule later on. We can use symmetry to identify, or rather classify, polyatomic molecules with regard to their moments of inertia. For instance, here we have a linear molecule, which can be a diatomic or a triatomic or indeed any number of atoms. If it is linear, one of my moments of inertia is equal to 0. I won't have a rotational axis around the internuclear axis of the molecule. But it doesn't matter where I put the 2 other rotational axes. Perpendicular to the internuclear axis, yes, but the angle between them doesn't have to be 90 degrees. It doesn't matter because the moment of inertia is always the same. So IA is equal to 0, and IB and IC are equal to one another. Why did I choose A to lie along the internuclear axis? Well, basically this is a convention, and the convention is the axis with the smallest moment of inertia is labelled as the A axis. So the A axis has the smallest moment of inertia, the B axis has the next smallest, and the C axis has the largest moment of inertia. So A, B, C, smallest to the largest moment of inertia. That is how we classify them. What about the next kind of polyatomic molecule? This is what we call a spherical rotor. It could be an octahedral molecule or a tetrahedral molecule. These are all spherical rotors. And the reason why we call them spherical rotors is because their moments of inertia around the 3 axes are the same. I think for something like an octahedral molecule this is obvious. However, for a tetrahedral molecule it is slightly less so. For instance, say I've got a moment of inertia through the C3 axis, it is not obvious that the 2 rotational axes which are perpendicular to that would be the same. But you could use symbol geometry to prove that for yourself. If you're not convinced, have a go at proving it. So, a tetrahedral molecule is a spherical rotor. Then we've got what are known as symmetric rotors. This is where one of the moments of inertia is different from the other 2. So 2 of them are the same and 1 is different. So linear is when 2 are the same but 1 is 0, spherical is where they're all the same, and symmetric is where 2 are the same but the third is non-zero. So what molecules are symmetric rotors? Well, molecules like ammonia, or a square pyramidal molecule, such as xenon oxytetrafluoride. These are what are known as symmetric rotors. And we can get 2 types. We can have, for instance, where the smallest moment of inertia is different from the other 2, or we can have symmetric rotors where the largest moment of inertia is different from the other 2. So when the smallest moment of inertia is different from the other 2, that is known as a prolate symmetric top, and where the largest moment of inertia is different from the other 2, that is known as an oblate symmetric top. And finally, we have what is known as an asymmetric rotor, where all 3 moments of inertia are different, where the moment of inertia around the A axis is smaller than that around the B axis, which is smaller than that around the C axis. They are all different from one another. This is known as an asymmetric rotor. It is by far the most complicated system to do, and we will not be discussing it any further. We will be discussing symmetric rotors. We won't discuss spherical rotors because, by definition, a spherical rotor cannot have a permanent dipole moment. Therefore, it is of no interest in rotational spectroscopy. So we will be spending some time on symmetric rotors, and I'll illustrate what I mean by prolate and oblate. So remember, we got our principal axes of inertia. They are located by symmetry, but there is a little bit of arbitrariness in how we define them. But it doesn't matter. You do have some choice, but it won't make any difference which ones you choose. The kinds of rotational wave functions and energies that we will come up with for the polyatomic systems will depend on the classification of that molecule, whether it is a symmetric top, whether it is prolate or oblate, or whether it is linear. As I've said, I'm not going to be discussing, or at least I'm not going to be giving you any examples of asymmetric tops like water, for instance. Water is an asymmetric top. It has a very complicated rotational spectrum, but we won't be considering it. Let's have a look at linear molecules like HCl, OCS and CO2. Here we have OCS, or carbonyl sulfide, a classic triatomic linear molecule that possesses a permanent dipole moment and so has a rotational spectrum. The A-axis is the internuclear axis, and around this axis the moment of inertia is equal to 0. The B and C axes are perpendicular to the A-axis and are identical to one another. The A-axis is the C-infinity axis, and of course is the principal axis of a linear molecule. IA is equal to 0 and IB is equal to IC. How about spherical molecules? I'm not going to be discussing these very much, but what types are there? Well, we have methane, for instance, which is tetrahedral, sulfur hexafluoride, which is an octahedral molecule, and then we have a C60 molecule, the Buckminster fullerene, which has an icosahedral symmetry. These molecules have no permanent dipole moment and are not going to show a rotational spectrum. However, just to note, the A-axis will be aligned along the principal axis, but of course the moments of inertia around the A, B or C axes are identical to one another. The choice of axes is immaterial. The axes are mutually perpendicular to one another. The moments of inertia are all equal to one another. So let's move on to the interesting symmetric tops. For symmetric tops, or symmetric rotors, we have two types. We have prolate symmetric and we have oblate symmetric. We'll first discuss prolate symmetric tops. Examples include methyl cyanide and sulfur monochloride pentafluoride. Here we've got a prolate symmetric top, phosphorus oxychloride. The axis is aligned along the principal axis in this case. It's not going to be an oblate symmetric top. It just so happens that the moment of inertia around the C3 axis for this molecule will be smaller than the moments of inertia around the B and C axes. This is not obvious. For instance, ammonia is not a prolate molecule, it's an oblate molecule. We will calculate the moments of inertia of ammonia in class and prove that it is in fact an oblate symmetric top. The thing is that unless you do the calculations, it is not obvious whether your symmetric top is prolate or oblate. You have to know the masses of the nuclei in order to determine it. I won't be asking you to go through that kind of tedious geometry in examination. I will always tell you whether the molecule is prolate or oblate. The B and C axes are perpendicular to the A axis. Now again, just to reiterate, the rotational axes go through the centre of mass, and in this particular example, not through the centre of the phosphorus atom. In this particular case, the moment of inertia around the principal axis, the IA, is smaller than the moments of inertia perpendicular to it. What about the oblate symmetric top? Well, here are some examples of oblate symmetric tops: ammonia, boron trifluoride, benzene, and the gold tetrachloride ion. The planar molecules are obviously oblate symmetric tops. Ammonia is not so obvious because it's non-planar. In fact, depending on the bond angle, it could well have been prolate. It depends on the geometry. Looking at benzene in a little more detail, notice the way I've drawn the rotational axes. The C-axis is associated with the principal axis because the moment of inertia around the principal axis happens to be the largest one this time. My B-axis and A-axis are perpendicular to my C-axis, but notice they're not necessarily perpendicular to themselves. The choice is arbitrary. I can make them perpendicular if I wanted to, but it wouldn't make any difference. The moment of inertia would be the same. If you're not convinced, do the calculations. I could have made the A-axis bisect the CC bond instead of being aligned along a CH bond. The moment of inertia would be the same as the one that goes through the atoms as drawn. The principal axis has the largest moment of inertia this time, so it is the C-axis. The A and B axes are perpendicular to the C-axis, but not necessarily perpendicular to each other. And this time, the moment of inertia around the C-axis is larger than that around the A and B axes, which are equal to one another. How about the asymmetric top molecules? In fact, the vast majority of molecules are asymmetric and have incredibly complicated rotational spectra. Molecules like water being one of the most important molecules you would want to study, but unfortunately having one of the most complicated rotational spectra, it is beyond the level of this module. Other molecules include chloroethene and hydrogen peroxide. So let's look at the case for the chloroethene. Although all the moments of inertia are different around the three axes, again the classification of those axes is the same. The A-axis is the one with the smallest moment of inertia. The B-axis and C-axis will be perpendicular to the A-axis, which will not necessarily be through the CC-axis as I appear to have drawn here. It would be in the direction for which the moment of inertia is the smallest. The moment of inertia of the A-axis is smaller than that for the B-axis, which is smaller than that for the C-axis. This is the end of part 2 of this week's online lecture. Please continue with part 3.